if you want.
Oh, okay.
Can I do this as well? All the announcements should be made by these. Also comments just for the recording.
And this is on?
On, and then off. And he's using wireless.
Sure. Yeah, thanks.
So, welcome to Semantic Big Data 2017. It's the second edition of this workshop. This year we received about 15 submissions, from which we finally accepted 8. We are very glad to have 2 excellent keynote speakers, Martin Theobald from the University of Luxembourg and Julian Dolby from IBM's Thomas G. Watson Research Center. First, I want to announce that there's an update of the program. So Julian's keynote is now scheduled to start at 11 a.m. And the presentations of Thomas and Petro are switched to session 3 and start at 2 p.m. and 2:30 p.m.
Is this an online program?
It's unluckily it's not in the online program because the program schedule was changed recently. Okay, I'm sorry about this. So let me introduce our first keynote speaker, Martin, to you. So Martin Theobald has been appointed as a professor of computer science with a focus on big data by the University of Luxembourg in 2017. He previously held positions as a professor and co-director of the Institute for Database and Information Systems at the University of Ulm and as a professor in the Advanced Database Research and Modeling group at the University of Antwerp. He obtained a doctoral degree from the Max Planck Institute for Informatics in Saarbrücken in 2006 and subsequently spent 2 years as a postdoctoral researcher at the Stanford University InfoLab. Between 2008 and 2012, Martin led the research group for ranking and uncertain data management at the Max Planck Institute for Informatics. His current research interests are focused at the intersection of information extraction, probabilistic databases, and distributed architectures. The Big Data Group at the University of Luxembourg investigates the whole life cycle of semantic data management, beginning with the extraction of entities and relations from textual and semi-structured sources and onto data cleaning aspects and probabilistic inferences. Martin is, of course, an area editor of some journals and a reviewer and PC members of many reputed international journals and conferences.
Well, okay, thank you very much for this very detailed introduction. If you wish, here's a concise summary basically of my past and current affiliations actually here. So I'm proud to say that I'm actually now, my job title officially is like a professor of computer science for big data. So nowadays it's no longer just databases, information systems as it is the classical way, but it's big data, I have to say. If you wish. So the title of the talk is Scalable RDF Data Management, which is basically a guiding theme for our works here. And the subtitle is here with a touch of uncertainty, which basically denotes like the second focus that we have here, still for a couple of years based on probabilistic databases. And this is a joint work with a bunch of my current and former PhD students and a postdoc here, Iris Miliaraki, which was with me at some point in time. So I'm starting here with our favorite application, which is basically information extraction here. So this is a well-known database researcher with a Wikipedia article here, in this case of Jeff Allman. And as you know, basically information extraction is basically about getting structured data out of various sources, partly structured, partly semi-structured sources here. Wikipedia has very nice properties that are exploited often for information extraction, such as these info boxes. It also has these categories and these kinds of things. So it's basically what information extraction endeavors such as DBpedia and Yargo do. They take basically these info boxes and create regular expressions and then parse these kind of logical facts, this RDF data here written in a logical notation here from these info boxes. So you know that Jeff was basically born here on a particular date. He graduated from Columbia and from Princeton at some point in time. His advisor was Arthur and so on. Now, basically, current work, there's also something we're doing at the moment, is more focused on doing a similar kind of extraction or getting similar data, RDF data, essentially out of these textual sources, in particular also of Wikipedia, which is much more challenging, basically, because you have to do all kinds of analysis here. You have to do text mining, you do some natural language processing, you have to recognize the entities in these textual components and so on. It's all much more vague in some sense, right, than getting the data just from the info boxes. But it's a very valuable source here. You get a lot of facts, a lot of additional knowledge about these entities here in Wikipedia in particular. And the goal would be here to get like similar data that enhances such an existing knowledge base. In other words, having new fact candidates about which you have to reason then if they're correct, if they basically fit into the existing knowledge base, if they're consistent with the existing data already, and these kinds of things. And what you often have here is also like something like a confidence value. Then there are different tools that basically provide confidences for their extractions, such as conditional random fields or hidden Markov models. So you often have something like confidence value attached. So this is basically where the uncertainty here of the data comes into play, and then we can see how we can further reason or work with that kind of uncertain data then as well. And that's a very valuable source here. So what you get from the info boxes here themselves is not actually that large itself. There's about 120 million facts here for Yargo 3, for example. This is the core of Yargo 3. Similarly for DBpedia. And most of the other components of Yargo or DBpedia, they basically consist actually of metadata, but not the actual semantic data from the info boxes. And then the hope would be that you get basically millions, hundreds of millions of additional facts just from Wikipedia, or you can apply these techniques to the World Wide Web, essentially then in a similar manner at some point, right? So if that's not enough data for you yet, it's about big data, of course, here, then I can show you this. This is probably one of the most frequently shown figures here in the context of semantic web here. This is the linked open data cloud, which has evolved a lot over the past years, has grown a lot, and these kinds of things. So this is definitely a case of big data. This is the current figure. They have a very nice visualization as of this year, I suppose, which basically includes all kinds of linked open data sources here, available from or linked from linkeddata.org, which now has more than 1,100 of these linked open data sources, which are all in some sense connected to DBpedia here in the middle, which is the main hub, right? To my knowledge, there's only estimations here how large this actually is. It's definitely very large. It's definitely in the order of billions of RDF triples, probably more than 50 billions of RDF triples, but it's basically a distributed database of RDF data here that is not available from a single site at all. And lots of old same as links and these kinds of things. So it's basically partially at least integrated data as well. I'm just highlighting two things here, two milestones basically in these knowledge-based systems to see applications of this in terms of question answering or reasoning with structured data, linked data, and these kinds of things that you get from these kinds of knowledge sources here. One is Wolfram Alpha. It's very remarkable. It basically comes from Wolfram Mathematica because like the number that they say on their webpage is even larger than probably the entire linked open data cloud. It's basically 10 trillion facts or more. It's a 10 with 12 zeros, unless I'm mistaken, right? There's a lot of stuff here, basically coming from all kinds of sources that Wolfram Alpha imports here. They have a lot of detailed weather information, for example, so they're basically archiving all kinds of weather data, but also like facts from the CIA fact book, Wikipedia, and all these kinds of things. And they have very nice visualizations and templates that basically display the results of your queries then. So you can ask, for example, compare Chicago with New York. So you get New York City, you get basically a nice map with Chicago, locations of Chicago, population of Chicago versus New York. And these kinds of things. Other things that you can ask them, obviously, based on the weather data that they archive is, for example, what was the weather of Tuscaloosa, somewhere in the US here, about 5 years ago. So they actually have this information, very detailed, like partly cloudy, the temperature range over the entire day, and you get these distributions and so on. But they don't know everything here. So here's a query that is a bit more specific. It's actually known or contained, the answer is known in Wikipedia. So asking here for when was the University of Luxembourg founded, that actually gives the wrong result. That says something about 1848 here, which is completely out of scope. So that's basically the wrong date. The right date would be like 2003. So University of Luxembourg is very, very young still, right? But nevertheless, another milestone here, and I won't say much about that, I suppose. We get more on that. And the next keynote here is IBM Watson here. The example is already a bit older, but I guess IBM is now, especially with Watson, striving into all kinds of domains, also like in the healthcare domain, medical domain, and these kinds of things. Remarkable question here is basically this one here, the clue that was gotten wrong by Watson at that time. was basically a major US city with 2 airports, one named after a World War II hero and one named after a World War II battlefield. That got the wrong answer by Watson. Watson answered Toronto. Do you know what it is? Since you're here, it's Chicago, of course, right? But at that time already, this is based on a paper that is already a couple of years old here, but at that time Watson used various knowledge backends, including Wikipedia, various web crawls as well, so they have like combinations of algorithms that try to find the right answer, but also like structured knowledge bases at that time already, including Yargo, I suppose. So here's the remainder, that's basically the introduction. Here's the remainder of the talk, basically striving through our areas of research here, which is basically exactly addressing these issues that I mentioned here, information extraction, something that we have like in terms of managing RDF data that is uncertain, that has confidence values attached, which goes into the direction of probabilistic databases, and then something on indexing RDF data and running Sparkle queries also in a distributed manner. So here's a nice example sentence that's actually like the one from the paper we had here. This is a TACL, so computer linguistics paper here. As David played for Manu, Real, and LA Galaxy, or La Galaxy. We don't know exactly what it would mean, right? So it's one sentence here, very short, abbreviated style here, and then the second sentence, his wife, Posh, performed with the Spice Girls, yeah? So what current tools for named entity recognition and disambiguation do is basically their pipeline. Yeah? So they use 2 steps basically, for example, using the Stanford NER tagger to detect the named entities that occur here, based on dictionaries, based on uppercases, spellings, and these kinds of things. And what we try to do here is to basically provide a joint model, a graphical model, probabilistic model that jointly does these 2 steps in one inference task, basically recognizing the boundaries of the named entities and disambiguating them, in other words, mapping them onto Wikipedia then in this case as a result of this approach. So here's basically one possibility for David. David is like the predominant meaning, I would say, of David in Wikipedia is probably this one, if you remember that from the Bible, right? This is the guy with the sling fighting Goliath or so, but it could also be this David here. So this is the disambiguation issue that you have. Yeah? If you look up these entities in Wikipedia, which is the most likely meaning here? And if you look at the context here in which that David occurred here with Manu, Real, and LA Galaxy, let's say, the more likely meaning, I would say, points into this direction here towards this guy here, right? Not to the guy with the sling here. Similar thing happens then for the next entity. This is like somebody, Manu, a Manu from the Indian mythology, I believe here. You can actually find that in Wikipedia. Or this one here, Manchester United, right? And this goes on here. So we have like Real, and then there's a very popular supermarket chain in Germany, essentially here with the same name, LA Galaxy, Posh, and so on. This one is actually difficult here because Posh here has a second meaning, Peterborough United Football Club, which is in the same domain as the other entities would be. So if you just go by the domain, if you think everything is sort of centered around soccer here, then the second choice here in this case would actually be wrong, right? And then obviously the Spice Girls and these kinds of things. So what you find here, or what you want to find, is this joint mapping, so the correct joint assignment of these labels, these disambiguated entities then in this case, with respect to all the occurrences of the entities and different kinds of features, including linguistic features and these kinds of things. So what we do here is we basically take a parser. This is a dependency parser here, the Stanford parser in this case. We get a parse tree of these entities. We basically try to impose a probability distribution over this. This is along the same lines as what would be done by conditional random fields, if you know this. So you basically have 2 kinds of variables here, the X variables. These are the observed tokens, the observations. They are invariant. They are given by the text, essentially, here. Then you have a bunch of labels. These are the Y variables, so they form a joint distribution, essentially, where you condition the distribution on the axis then. And the labels are the ones that you want to find. Now, this could be David Beckham or David from the Bible or something like this here in this case. And then you have like this nice formula, it's a very generic formula for modeling like these kinds of like factor graphs in general. So you have these factors that are among the labels. Actually also like there would be factors here which are omitted in the figure between the tokens and the labels. And they give you basically the feature functions. They tell you, is this like occurring in a dictionary here as David here? Is it a word in uppercases? Then it's more likely to be a named entity and these kinds of things. But we also have a lot of like linguistic features in there. So like seeing like that you basically have different verbal phrases here or prepositions, for example, like played for from these dependency path trees that give you additional hints on the disambiguation. And this forms basically a graphical model essentially here. And then hopefully in the inference, which you can formulate as this argmax problem, you find basically the most likely assignments, the labels here, these y's, given the x's, right? So then this would be your disambiguation. Hopefully that works then correctly. But here we basically perform two tasks in one step. This is the joint disambiguation, hence the idea here with this joint named entity recognition and disambiguation task here, which also gives you this nice acronym here, NERD then in this case. So for these tree-like or sequential structures, sequences basically of tokens as in sentences, this works very nicely. Also like for the inference here, this is generally a difficult problem in these graphical models here. For sequences or trees, you can find an exact solution using some dynamic programming here, in this case Viterbi algorithm, for example. You can further augment this as well. You can basically impose such a graphical structure over multiple sentences, taking co-occurrences of entities also into account. For example, if you have a David here and a David there, they might denote the same meaning, so they have like a coherence edge in between. This is another factor which basically expresses like the similarity between these entities then in this case as another feature function which goes into the formula. But then you get a more general graph model. It's not just a tree or like a path anymore, a sequence. It's basically an arbitrary graph, and then the inference becomes much harder. Then you have to do some approximation, typically some kind of sampling or Markov chain Monte Carlo technique here for the actual inference task, which is this one here. So this basically improved over previous versions here. We have like different approaches from different groups. AIDA is from the same group at Max Planck than the work here by Janiot at the time. TAGME is another group like from PISA, I believe, and Spotlight is the one from DBpedia, actually from Chris Beetzer here. So you improve with the joint approach over also like some pipelined approach. This would be this one, about like let's say like 1.8% here in precision or 1 point something percent in combined precision and recall, which was actually significant here for that ground truth collection in that case. So I also try to point out some PhD challenges here after every part of my threefold talk here basically. So here would be a nice case, nasty case let's say, that currently I would claim is not handled correctly by these tools here, by neither of the ones that I had on previous slide. Paris Hilton stays in the Hilton in Paris. So what would be the right entities here if you think about this? This is being like disambiguated, the recognition of the entities, the boundaries is okay, of course. It's easy because they're all in upper cases. But the disambiguation actually goes wrong for all of these tools. Here's an example from the AIDA online demo, essentially. Paris Hilton stays in the Hilton in Paris is disambiguated to the most coherent mapping, to the most similar mapping among all the possible entities you can assign to these, and that's 3 times Paris Hilton. Yeah, that's probably not correct. Yeah. That happens all the time if you focus too much on coherence, onto a joint disambiguation here, which basically finds the most similarity among the entities that occur. Self-similarity is, of course, the highest here. Humans, however, usually get this right. So what would you think is the right disambiguation here? Right? Be more like something like this. The entity, the first entity would be the person, Paris Hilton here, then the hotel, and then possibly the city of Paris. It also works similarly with Chicago, but then Chicago is actually easier than Paris because it's like a different name, of course, yeah, in the last part here, if you exchange this with Chicago. But it's possible for humans, it's a bit contrived, but it's possible for humans to assign this because you see the verbal phrases, right? You see stays in, yeah? Stays in is a relationship among maybe a person and a location or something like this, but not among a person typically and another person, not even herself then in this case. It's not a reflexive relationship either, not symmetric, neither reflexive. Yeah? So these things you can take into account, so you basically have to encode that in a better manner into your graphical models or your generally your disambiguation approach, I would say, right? That's my ultimate PhD challenge number 1 here. Okay, with this we are switching slightly the topics. We're going into uncertain RDF data. This is the motivation part from before where you have these confidences attached. This belongs to a general domain that is called probabilistic databases in some sense here, if you wish, but it can be applied to many things, also in machine learning and in AI. Probabilistic databases have the nice property that they're running SQL, however. So here's in general what a probabilistic database basically is. It's nothing else but a probability distribution over a finite set of possible instances of a database relation, or a set of relations even. So here we have one relation basically telling us where somebody might work. Here's our Jeff here basically. He could possibly work in Stanford or Princeton. That's one possible instance, and I'm just writing a probability to it, right? But Jeff, in another instance, might only work for Stanford, not for Princeton, right? So then we have an instance where Jeff only works for Stanford, or another vice versa instance where he only works for Princeton, and then he doesn't even work at all for anywhere, or doesn't maybe even exist. That's the empty instance here, that also has a probability attached. This is basically here the case when we have two tuples in our regular database, which we basically blow up into four possible instances, basically taking all the subsets of these two tuples here in a probabilistic manner. Just attaching a probability distribution that sums up to 1 makes this a probabilistic database. That's of course way too expensive to do this. For 100 tuples or so, I wouldn't want to enumerate all these instances anymore. Let's say we do this in a smart manner, in a compact manner. We can basically choose this extreme case. We can have a tuple-independent probabilistic database. Rather than writing probabilities to the instances, we're writing probabilities to individual tuples. And then we're making an important assumption here that we're basically saying these tuples are independent then. So in this case, we say that maybe Jeff just works at Stanford with 0.6 probability, but Princeton with 0.7 probability or so. And then we have nice properties here. So you can basically say, what is the probability that Jeff works in Stanford overall? Yeah, you can basically look at the probability here, 0.42, plus the probability there of these two possible instances that encode exactly this case that he works in Stanford here, and that sums up to 0.6 as well in this case. Yeah? That means if I choose the weights here accordingly, in the same manner as I would get it basically under this independence assumption, I'm actually encoding the same information, the exact same probabilistic database here in a much, much more compact way. Yeah? So I don't have to go through this exponential blow up in this case. But this world here, this representation can capture correlations among tuples. I can say certain tuples, certain combinations are more likely than others. This one cannot. This only works with independence assumptions. There's another important building block in probabilistic databases where you have something like block independence essentially here, and then you can also say we're relaxing this complete independence assumption a little bit. We basically have something like tuple alternatives here. Oops, we can say that Jeff works either in Princeton and Stanford or in Princeton, and then these blocks internally form something like a probability distribution. But that's not the same anymore as these two then. This is a different kind of a distribution that I described at this time. And then the query answering problem is very quickly formulated, but it's very expensive in general to compute, basically. So what we do here for query answering is we want to compute something like marginal probabilities without any further conditions. That would be these probabilities as well here over these possible instances, but for entire queries. Yeah? So we run a query here conceptually at least against each of these instances, and then we take the sum of the probabilities of these instances where the query answer exists. Yeah? But then for this definition, we basically have to go for this. But most of the probabilistic database research basically focuses on answering the queries over this representation. Yeah? So I have a small flashback here because it's a very interesting topic, or exciting topic also for me here. Historically here, this is like a back pointer to something that was done about 12 years ago by Jennifer Widom here, proposed by Jennifer Widom, essentially here published in a CIDR paper from 2005. It's a Stanford trio system. Very nice features here, basically the first probabilistic database in historical terms, let's say, that had a unified data model for uncertainty and what we call lineage here of databases. They have different features here. This is like tuple alternatives, so they can basically encode like alternative values for tuples here in their model. They had maybe annotations, so possibly missing tuples in the model, and confidence values, which would then be basically the more recent term that we understand here, denote the case of more recently, what we say as probabilistic databases then. And lineage basically, which interconnects all these kinds of features in a unified data model. So here for the uncertainty, we can basically say we have an uncertain relation. It's like actually like a block-independent probabilistic database then. We have Amy having seen a red Honda, a red Toyota, or an orange Mazda. These are exactly three alternatives here of this probabilistic database that we can have. They're mutually exclusive, so we get three possible instances in this case. Right? This is what we called a green table at that time. Then we have maybe annotations. So in addition to these tuple alternatives, we can write a question mark to these tuples. We can basically say Betty might have seen a blue Acura or nothing at all. So this tuple might actually be missing in the database as well. So with this together, we get 3 alternatives here, 2 possible conditions or states here. So we have like 3 times 2, 6 possible instances, right? And then we have the weighted case, is similar to before, but we have weights attached. So we have 6 possible instances here as well, but each coming with a probability. And this is exactly what we called a block-independent probabilistic database on one of the previous slides here. Yeah, but now we can weigh these kinds of uncertainties in a more detailed manner. The problem here is that these things need something else. This is by itself a nice model, but it's not closed. So the result of relational operations over this cannot be represented as such correctly without any further mechanisms. We need something that we will call lineage here. Here's a query here basically looking for suspects of possible crimes here where people are possibly witnesses of a crime here. Like Kathy might have seen a Honda or so, or something like a Mazda in this case. 2 possible alternatives, and people driving the respective car then possibly. That would be Jimmy driving a Toyota, or a Mazda, and Billy driving a Honda, or Frank driving a Honda, and then Hank driving a Honda for sure. That has no other alternatives. So if you try to find suspects, it's just a natural join basically over these 2 relations here. And then we get something like this here. So we see that Jimmy might have been a suspect basically if Kathy saw the Mazda, and Jimmy might actually have been driving the Mazda, and so on. Yeah? The problem is here that we don't actually have like all possible combinations, so like 2 times 3 times 2, like 12 possible instances in the result, but actually much less, because these answers are interrelated with each other. That doesn't correctly capture all the possible result instances here and cannot even do this. What we need here is basically what we call lineage. We have to trace exactly how these query answers were derived when Jimmy actually is a suspect, namely when Kathy saw the Mazda and Jimmy was actually driving the Mazda. So we trace these lineages here as Boolean formulas for all the possible query answers, all the alternatives here. And then we can actually exactly capture what the result instances would be. It's only going to be 4 actually rather than 12. This actually, with the lineage, not that obvious, but with the lineage, we can actually capture all the possible result instances. Basically, if Jimmy has basically seen the Mazda, Kathy has seen the Mazda and Jimmy has been driving the Mazda, then Jimmy is a suspect. Otherwise, he's not a suspect, so then he doesn't co-occur with any other entities. If Kathy has seen like the Honda or so, then either Billy or Frank would be a suspect, and together with Hank in this case. And if Kathy didn't see the Honda either, then we have an empty instance as well. That's basically 4 possible instances. That's what we call the operational semantics at that time. That's what all probabilistic databases basically exploit. So rather than going this downward way here by enumerating all the possible instances and then running the query on these instances, we try to find something that is actually like called a direct implementation here through the lineage. We basically run the query on the actual normal database, but we basically trace the lineage to also then compute the probabilities of the query answers in this case. This has very nice properties for a database system. This basically gives us a closure of the operations, so you can show that all relational operations over this, including the lineage, then are actually closed. That's a very important property. And even more strongly here, you can say that this is a complete representation model. It can capture any set of finite set of possible instances here at least that can be represented in this model. However, there's a small caveat here. So basically the data complexity, even if you go this direct route via the lineage here, remains very expensive. The data complexity is sharp P, which is an exponential complexity class here, also over this model. So you basically push everything into the confidence computations rather than into the actual data computations here in the lower path. We're coming back to this in a few slides again. So this is basically the main result here. This model here, which is now common in all probabilistic databases, approach is closed and complete here, and we started more properties here, like minimizing this, finding extraneous tuple, removing unnecessary tuples, approximating things, and these kinds of things. So what does this have to do with information extraction here? To close the gap to the previous part here, basically. Very popular example here from the real world, maybe. If you look at this Wikipedia article by Barack Obama here, you can basically find out, for example, that he might have been born or is born in Hawaii, Honolulu, Hawaii, which is in the US, which made him eligible to be a US president. But it turns out there's also like an actual conspiracy theory article in Wikipedia itself about Barack Obama, which mentions all kinds of false facts about Barack Obama, of course, as well. And there you might actually then find that he might have been born in Kenya. Yeah? So for humans, this raises like directly an inconsistency. You see that these two facts cannot be true at the same time, so you have to basically figure out which is the correct fact. Yeah? And this is something we try to reassemble in some sense here as well with our techniques in let's say, a probabilistic database context. What happened in the real world was that people in the White House, they released the birth certificate of Barack Obama at that time, and that should then basically increase the confidence for us to believe that it was indeed Hawaii and not Kenya. Yeah? So what we can do here is we can basically formulate now different kinds of rules, which is something that you probably well know from also semantic web contexts here. We can have like rules like these here. We can basically write implications. This is actually data log style notation here. Slightly more logical notation, but it's a data log rule essentially here. That gives us an implication here which tells us that people might actually live where their spouses live. So if you don't know where a particular person X lives here, but you know where the spouse of X lives, then you can infer from that living place of the spouse that person X also lives at the same place. That's not certainly true for everybody in the real world, so these are also probabilistic rules in some sense. Another rule here would be even more vaguely that people live where their children live. If you don't know where somebody lives, you could still find the fact where the children of that person live, basically, and then do a respective inference, right? So these could also be expressed in terms of probabilities here, wherever they may come from in this case. And then you have a second class of rules which are more like consistency constraints. It's also very expressive to something we need to reason about these inconsistent birthplaces, basically. We can say that people are not born in different places. So if you have like a rule which says X is born in Y, and X is born in Z, then these Y and Z arguments should be the same. If they're not the same, if you happen to have two different birthplaces as facts in your knowledge base, then you have to set one of them to false to make that rule true. Yeah? So that's another way of reasoning. It's actually a functional dependency or so-called denial constraint in databases. And you can also add a temporal component to that. You can basically say, if you have the case that somebody, like a person X, is married to multiple people, so Y and Z are not the same in this case, then these marriages, these facts about the marriages should at least be disjoint in time. So you can add another dimension here, a time interval or time points, essentially a set of time points here, such that these marriage facts are true only when the time points are not overlapping, essentially. Yeah, that's also possible. So this relates to a lot of things you can do in databases. This is the core of SQL, data log anyway, also relational algebra, select, project, join queries essentially here. That also comes up in the semantic web in RDFS reasoning, special case thereof essentially here, all 2RL different standards. And here you have more constraints here basically, or could express like functional properties as well if you wish. So here's an example, a detailed example now for how to process such a query now, very detailed query, over such a setting. We have basically these base facts here from our information extraction techniques with confidences. We have rules, like a soft rule and a consistency constraint, like a blue rule here. The soft rule basically says people basically graduate from where their advisor works. So if you have a rule, here's a rule basically that says, if X has an advisor Y and Y works at Z, then X actually graduates from Z as well. And the constraint here for this example says basically people should not actually graduate from multiple places. So if we ground this query, so we're now asking very specifically, where did this person here, X being Surajit, our head of research here from Microsoft, who gave a very nice keynote two days ago, basically work here, or where did he graduate from? You find basically two base facts that indicate either Princeton or Stanford in this case. In this case here, at this time, Princeton is actually more likely to be the right answer from the given base facts. But you also have this rule structure which you can ground. This is actually the lineage structure that we get here from grounding the green rule at this time. So we have a conjunction here from the body of the green rule, which gives us one more time the hint into the Stanford direction here. So we basically have a disjunction with the base fact from the head of the rule here, which basically says either this rule is true, and then it's actually Stanford, or the base fact itself is true, it's also Stanford. So we basically get a push towards the right-hand side answer in this case, right? Then the blue rule basically gives us this tension here between the two places. This is this mutual exclusiveness here among the two graduation places here in this case. And then you get the two answers with their Boolean formulas basically encoded here as the lineage structure, right? And then in some cases, hopefully, you can do a very nice inference now. You can basically use these confidences, these input confidences to compute these marginal probabilities here for each of the query answers. You can basically sum up all the probabilities of the possible worlds here conceptually very efficiently by exploiting these independencies. So if you have a conjunction here, you basically just multiply these input probabilities if these two things are independent, right? If you have a disjunction, you can do a respective independent OR operation also for the disjunction. This looks like this here. It's just an application of De Morgan and the conjunction then in turn. And then you get basically with the mutual exclusiveness here on top, you get basically these results. Yeah? And that's much faster than summing up the probabilities of all the possible instances. However, that only works if you have these independence assumptions working all the way down from the query answers back to the base tuples. If there's like a cross intersection or a cross dependence, if it's a DAG structure rather than a tree structure, let's say, then that doesn't work anymore. Then you have to do something like this here, at least conceptually. You can basically write a truth table where you basically assign a probability to every possible world here, to every such thing here. That's a possible world semantics here. So you take basically all the tuples here, all these variables with their confidences that are true under such an assignment, such a possible world, and multiply their probabilities, the input probabilities. For those that are false, you basically take 1 minus that input probability, and then you get the probability of that possible world, right? And that forms a distribution, and statistics is nothing else but a binary independence model, basically. And over that distribution, you can then basically look at what is the marginal probability of such a Boolean formula. This is like the formula for the second query answer here that sums up over these possible worlds to exactly the same probability here. Works always, but is of course much more expensive. Yeah? So this truth table grows exponentially, essentially here. This is the sharp p hardness, essentially. Same for the second query answer. Then you can do more tricks. You can condition here more if you also encode a hard rule, this consistency constraint that he didn't graduate in multiple places. This is the formulation thereof. You can basically prune impossible worlds. So you get a conditioning effect. So you typically raise the probabilities and these kinds of tricks. Unfortunately, for most exciting queries, the sharp p hardness actually strikes you quite a bit here. So here's a fairly simple query over a database here with 3 predicates. Is professor, works at, and located in. So if you run this query, again in data log notation here, this is actually data log notation. If you want to find people, or the answer is a Boolean query, is there a professor who works in California, at a university that's located in California? This basically join among the 3, and then you intermingle all the different possible answers here to get the answer yes or no for this Boolean query. This is actually a pattern that is not hierarchical. It's a DAG structure here. So this goes into two different ways here. That's known to be sharp p hard. And that's unfortunately, for most interesting queries, the case. So you need some kind of approximation here as well. So there's a lot of literature here in terms of approximating or calculating query answers in probabilistic databases. One is on knowledge compilation here. So if you have like safe query plans or read-once formulas, these are the good cases essentially, then you can do this directly in SQL. Otherwise, you have to come up with some tricks here. So knowledge compilation using decision diagrams, OBDDs, or more recently SDDs, sentential decision diagrams. This is an important way here, exploiting these independencies whenever possible, or doing some kind of top K pruning here by looking at bounds for these queries, for the confidence of the query answers without knowing the actual probabilities actually even here. And this is also something very nice that you can do here. You can basically say, okay, we're grounding this now incrementally, top down, same query as before, Surajit graduated from Y, we're looking for possible Y answers here, without grounding everything down to the base here in this case. So we stop at some point here. So after basically looking for the base facts, there's still this rule left, which basically says you basically graduate from where your advisor lives, which creates possibly large lineage structure underneath. But before grounding the rule here, which can be a very large lineage underneath here, you basically try to come up with a bound here for these possible answers as well already. And then you try to prune basically as soon as possible before you actually have to go basically further down into the data. So what you get here essentially are first order lineage formulas. So you have basically a fully grounded formula. It's just A, this one here, for the first query answer, just the disjunction over A, which is still A, and the disjunction of B, the second query answer, with everything that can come underneath here from this open subgoal, which we haven't evaluated at the time yet when we do a top-down search, right? And here the interesting idea is that we can basically compute a bound here by a smart, clever substitution of these open subgoals. So we have a formula here with an open subgoal, even existentially quantified and these kinds of things. So a lower bound here would be basically saying, so we have also sometimes some theorems here, but I'm just doing the interesting parts here. A lower bound can be obtained by basically substituting here this open subgoal with a constant false. Then the formula just breaks down to the probability of B here Looking for the probability of B is easy. We have this already, so lower bound at this time is 0.6. Yeah? And everything else, the more we know about this open subgoal, will only increase that probability later. Vice versa, for the upper bound, we can basically substitute, instead of false, we can substitute with true for the upper bound, sorry. That's a very simple upper bound at the time. This is the most general upper bound. It's just the probability of true, which is 1.0 here by definition, right? And you can actually show that this works for all kinds of cases you get from this kind of grounding procedure. You can show one more thing, namely that these bounds converge gradually. You start with the most generic lower bound. Probability of false is 0, essentially. Then the probability of false or something will increase. It's the 0.6 from before. And then eventually it would actually go here to 0.88 here in the final case, let's say. And the other side is actually the same, then actually also converges then eventually to that bound, if you keep on grounding. And that works for all kinds of formulas that you can get from this grounding procedure, which is the cool thing that we showed here at that time in that paper. Then you can wrap these bounds into a top K algorithm. This is also often understood by, or denoted as Fagin's algorithm here. If you have a bunch of these bounds, so query answer 1, query answer 2, 3, 4, all with the lower and upper bounds here basically, if you have this case, if you're looking for the top 2 here, that's the second best lower bound is already larger than all the other upper bounds here, then you can stop doing this. Yeah? Then you have safely found the top 2 answers here with these confidences. Computing the exact probability, which might be somewhere here in the middle, is sharp p, but often we can find these top 2 answers here in an exact manner, the set of the top 2 answers here, without basically going all the way down into the exact lineage. Yeah? We can also append this to a more probabilistic temporal database setting. So if you basically have confidence intervals attached to base facts with time intervals, it's also something you can often extract. So Wikipedia has these time intervals attached, for example. You see basically that like Beckham might be playing for Real in 2003 to 2005 and then 2005 to 2007, depending on how you extracted this with different confidences. The same happens for Ronaldo playing for Real here, different time points, different confidences, and then you have a rule, basically a query in other words, which says when are they, or asks for when are these guys actually teammates of each other? When is the intersection of these intervals true, and which confidence does it then have, basically? Yeah? So you can split or align these intervals basically as you go through these input tuples then, and compute these confidences. So you want to find basically all the time points here in the answer for when the answer is true with their respective confidences. So here you have to look at the overlapping time intervals, do some alignment operations which are common in temporal databases as well, and then you get like a nice confidence distribution here, also for the query answers here in this case. So this is like a combined temporal and probabilistic database model in this case, which you can also show that it's closed and complete similarly to before. And yeah, this is the answer here. So if you basically do this for many answers, for many facts here, even if you assume that the input data is essentially independent, the answer tuples, of course, when these people are teammates here, they are no longer independent because they operate, they are generated over the same input data here. So this is now a closed and complete representation model with the lineage for probabilistic and temporal databases here. And the good news is basically that these temporal alignment operations, finding these intervals, this is linear, and, or at least sorting. You can do the sorting linear time here, which actually applies here quite nicely. Linear in the number of input intervals. But the inference part, probabilistic inference here, calculating confidences for the answers is still sharp p, of course. All right? Here's my ultimate PhD challenge. That's something we're actually working on. So basically providing these kinds of confidences and probabilities for arbitrary SQL queries. It's a form of inference that is called lifted inference, essentially in machine learning here, is really like grand challenge here that we can formulate maybe. So doing these kinds of inferences here, say for queries like where did Surajit graduate from, in an arbitrary manner for conjunctive queries, for other queries that you have basically on the fly. That's a really cool application. So you can refine these bounds. You see that there's like a 0.7 here, the interval converged, and there's a 0.88 here, interval converged, so you can give the query answers and so on for arbitrary queries. How much time do I have? 10 minutes? That's perfect, it's fine. The last part is a bit shorter though. And here's just a counter example for Boolean queries then as well, just saying, yes, he graduated from somewhere, that's like another disjunction on top. All right, the last part on RDF is a bit shorter though, I have to admit that, so we're a bit passionate about probabilistic databases sometimes. So RDF and Sparkle, I don't think I have to tell you too much about the data model. It's just a very nice generic data model. It has a lot of interpretations. It's relational data. It's one big table or many small tables if you basically partition by the predicates or so. You can interpret it as logical facts and then apply data log to it or whatever you want. Or you can look at it as a graph, directed graph with a unique name assumption essentially here. Similarly, Sparkle queries, they are basically interpreted as relational joins in literature often, if you come from a database background. Typically conjunctive queries over these first order literals here, if you want. If you look at the Sparkle, these triplet patterns, these are conjunctions of these triplet patterns, or even as subgraph isomorphism queries, if you wish. Like just pointing out here, looking for people who are born in the US and want some reward. The data complexity of Sparkle, the core of Sparkle here, is good news, is always polynomial. So just looking at the data, increasingly large data stays polynomial. So it's not as bad as probabilistic databases, of course. So you have to just figure out how to find these embeddings efficiently then. Just basically saying. The combined complexity on a side note here is always exponential. Or if you have recursion or these kinds of things, is always bad here as well. So what we did here in Triad, this is our RDF engine from 2 years ago. Essentially here is a master-slave architecture essentially. So we take basically incoming RDF triples from an RDF collection here. We parse the RDF triples and we index the data essentially here. We have like a dictionary encoding for the triples. Most remarkable thing here is that we also create a summary graph for the RDF data that we get here. So we can summarize this very efficiently, compactly, and store that summary basically at the master node of this architecture then. And then everything is basically sent through the network, through a number of slave nodes here. Using message parsing, the slave nodes create the local indexes over the respective graph partitions. So they create disjoint partitions here basically of the graph data. And then create also these SPO permutation indexes, which is very common in RDF indexing in general. At query time, we basically run through the master node. We run the query first against the summary node. So you can prune a lot of data based on what is not important based on the summary graph already. And then we send the remaining partitions, the partitioning information that is important basically to the slaves here, and only very selectively process the actual query, the full query then, against the indexes at the slave nodes. So almost a classical master-slave architecture in that sense. However, at query processing time, all these slaves here, they can directly communicate among each other. So this pipeline here basically goes directly through, not just from the master to the slaves and back, but basically directly also among the slaves at query time. Just a quick note here, what we usually do is a locality-based partitioning using Metis, for example, is a very popular tool for partitioning large graphs here. So you essentially try to find a min k cut, like k partitions that are evenly sized, either in terms of number of nodes or edges that they contain here. And then you find a cut here such that the number of cut edges here typically are then minimized among the partitions, which is good basically because the less edges you cut, the less communication you typically need at query time, at least for certain kinds of queries which exploit this locality-based partitioning then as well. Yeah? So if you have the summary graph, looks like this here, we basically put all the nodes in the summary graph, like Barack Obama, Democrats, Honolulu or so, into that one graph partition and basically forget about that. Yeah? So we don't otherwise keep the internal contents of these partitions anymore, but we have the edges basically that connected these partitions. Yeah? Among the partitions, here like one and type and so on, but also we introduce self-loop edges among all edges that occurred inside such a partition. So we can basically run an arbitrary Sparkle query also against the summary graph here. Yeah? So we're storing this in the form of a dictionary, and then when the query comes in, we basically first run it against the summary graph. So Barack Obama belongs to partition 1. Located in gives us basically two connections to partition 1 and 2, and even like a self-loop edge, I believe, here as well. So these are the relevant partitions, and then we can basically see if there's also like a connection with a 1 in edge here from P1 to P2, and not to P, oh yeah, there is one here, to P4 as well. So you can basically do a lot of pruning. We basically know, based on this, that all the remaining partitions, in this case only one, in reality it's typically much more partitions, are never going to be relevant to answer that query. So we never have to look at any data that belongs to these partitions. Yeah? And we do an over-partitioning. We typically use much more graph partitions here than there are compute nodes in the network. Another nice effect is that if you have like an impossible query condition, like a governor here, governor edge here, that is not contained anywhere among the matching partitions, You can basically find this out directly at the summary graph in the master node without going into the slaves at all, which is also a very good feature of pruning here. So we can say this query for sure has an empty result. Yeah? The following is basically a very classical database approach. We compute a query plan using all these kinds of available information about which slaves contain which predicates here, which we sharded. We use this locality-based partitioning here for sharding in this case. Which partitions are relevant based on the summary graph, and we have some cost estimates, so we basically put this into a dynamic programming algorithm for join order optimization here in this case. And we use basically a parallel approach, so we can basically say that this branch of the query plan here can be computed in parallel to this branch of this query plan because of the distribution. So they're running freely in parallel then at that time here, just over disjoint partitions of the data graph, right? So we have a cost model that basically takes the maximum over the subgraphs into account here, rather than the sum in a classical approach. And we're sending essentially the same query plan, which we computed here in the master node once, to all the slaves. All the slaves process the same query plan, but over disjoint partitions of the data. Yeah, so we have basically like an index scan here and the lower parts here at the leaves. Then we have a merge join. D stands for distributed, so distributed merge join. And then the last part, a distributed hash join, which combines the data from these partitions again. In some cases, we need resharding, but not many times. So we can spare a lot of the communication if we do a clever partitioning here at query time, essentially. And then we run the query plans, so to speak, here in these parallel iterations here. So this is basically one thread on one partition for slave 1, or on slave 1, another thread on another partition for slave 2, and then basically combining them, synchronizing them only when necessary. So most of these paths here can run freely in an asynchronous manner, which is very good if you have a large bushy query plan, essentially. In this case, if we shard on the subjects, for example, we might need some resharding. So this is redistributing the data at query time, but not many times. So it's typically selective queries, so not too much data has to be reshuffled through the network, and then also like in the following steps and so on. So I think I'm quickly skipping over the experiments for the interest of time in this case, coming to a summary here. So we compared to a lot of engines and so on, worked well. So we were up to 4 to 5 times faster on average than existing prototypes at the time. Here's my ultimate PhD challenge, maybe worthwhile mentioning in the end here. So what we have seen in the past are these kinds of architectures, also for distributed RDF data management based on map and reduce. So you have these single iterations, like in Hadoop, everything is file-based, you have HDFS underneath and then so on. So you basically have to reshuffle the data, you need synchronization in between these phases here. This is the shuffle and sort phase. In map reduce environments, essentially, what we nowadays see, like in Spark or Flink here, is more like a main memory-based architecture where you have these entire data flows. Yeah? But the data flows with many complex, possibly complex operations in between, they are still synchronous. So you have to reshard here all the time among these iterations for the first transformation and the next transformation and so on. And then eventually it goes to files. But in between it stays into main memory. So getting rid of these synchronization points in between here, just like pushing the data through the compute nodes as much as possible, like in a pipeline approach here, that is basically what I would highlight here as an ultimate PhD challenge number 3 in this case. It's my last slide. I think I'm on time still, at least I believe I'm on time. These 3 areas that I mentioned here, information extraction, natural language processing techniques, named entity disambiguation, recognition, also relation extraction and these kinds of things here, combined with uncertain data, various probabilistic or temporal models that you can have, making this inference here more scalable, and also finally combining this with big data techniques like distribution, whatever we teach, also big data analytics with various machine learning libraries and these kinds of things. Combining this, so the intersection of these 3 areas, I think is a hugely exciting research topic and probably material for many, many PhD theses in the future as well. All right, that's my last part. I have some references, and that's the end of the story.
So thank you, Martin.
We can leave this on.
So we are the first time live streaming, so every question should be also directly speaking into the microphone. Just to, just to tell you this. So are there any questions about this nice talk of Martin?
Hi, this is Pedro Zekeli from the University of Southern California. Yeah, so very interesting talk. Thank you.
Thank you.
So I had one comment and one question. The comment about your Paris Hilton. So there's a Paris in Texas, and there are many Hiltons in Paris.
I see.
And there are, of course, probably more than one Hilton in Paris, Texas. So
Right.
it's a set of answers in a sense. No, there is
Right.
no single answer. The other is a question. So we work with investigators from law enforcement in also working on knowledge graphs extracted from data, and they are not interested in confidence numbers. They are interested in knowing why they should trust the answer.
Right.
Maybe going back to the original sources. So show me where this was extracted, or how this answer, why should I trust this answer rather than, it's 0.8. And, the guy says, at 0.8, I still need to get in a car and go sit outside somebody's house for many hours. I want to be sure.
Yes, yeah. Well, maybe I can comment on your comment first. So with the many Paris Hiltons and the Texas thing, I think for a given instance, for a given text, maybe a tweet or so, it really hugely depends on the context where that occurred, right? So typically people, when writing something, they have a unique meaning in mind, and the trick is to find out this particular meaning. So typically people do not want, at least in most cases here, write something that is ambiguous, but it's just depending on the context. So if you know that that person was maybe in Texas rather than in Paris, maybe that is the context that you need, but it's of course from a broader scope. And the other thing is basically, I mean, we don't have a system that implements all of this in one piece, of course, but potentially the components are there, right? So you can trace the information. You can basically keep where the text data, or keep the text data where the information was extracted from, and then point to that. And then in turn, this gives you more context and more ways to reason about the sources, if that's a trustful or not so trustful source, and what happened there. That's exactly the lineage thing that we potentially have, right? And it's also easier to basically do this at query time rather than to pre-compute everything, because you basically can keep up to date more with the data. If you call the web or if you get new tweets in, you can basically incrementally do this, and then at query time you basically give the most recent answer to the user in that sense. So conceptually, all of these things, I think that they include many things that are highly exciting for many approaches. But yeah, so I still need more students to implement all of this in one piece then in the end, of course, yeah. But I think it addresses many things. And actual confidence, like 0.9 versus 0.88 or so probabilities, they're not relevant at all, really, that's true. But you can use it for ranking very nicely, right? So they're basically, yeah, they're high, at least expressive ranking models. Probabilities are more, I would say, expressive due to their combinatorial complexity also. That's why they are so expensive than just rather simple confidence aggregations in the end. But you don't need the actual value in the end, of course. But you can use it for ranking, and you give the most confident answer. You choose the most likely answer, or these kinds of things. And you can find also like things that are just not making sense together. So you have these constraints attached. So you can say, okay, this is the single most likely answer versus another answer that makes no sense. So the combination of these rules and everything is also, I think, a very expressive setting altogether.
Are there any other questions? Okay, then thank you again, Martin, for this very nice talk. And I want to introduce the next presenter to you. That is Daniel Janke. Daniel Janke is a PhD student in the Institute for Web Science and Technologies at the University of Koblenz-Landau. His research interests include data placement and querying strategies in distributed RDF stores. More precisely, his work examines the impact of the data placement strategy on the query execution effort. So, and he will have a talk on data placement strategies in distributed RDF stores.
Thanks for the introduction. My today's talk is on data placement strategies in distributed IDF stores. Basically, distributed IDF stores are required since, for example, in your previous talk, we have seen that there are currently data sets with more than 10 trillion triples. And basically, a distributed IDF store is a graph database which is distributed among several compute nodes. In this example, you see a distributed IDF store which consists of 2 compute nodes, and the example graph stored in it consists of 2 institutes which have several employees with the corresponding names, and there's also a dog which is owned by 1 employee of 1 institute. The changes in these distributed IDF stores comprise data placement strategies, then the distributed query processing, and also the handling of failures of compute nodes. My research focused on the data placement strategies in these distributed IDF stores. Basically, if you now want to execute a query, like the one given at the top of the slide, this query wants to extract the institutes and the names of all employees in the different institutes. If you then execute this query against the distributed database, then we can see that we find 3 matches for this query. One match consists of these orange 2 triples in the compute node 1, and there exist 2 matches in the compute node 2, which are these blue triples and the green triples. Basically, the performance of these distributed database consists of how huge the data transfer is. This means if an answer of the query requires that data needs to be shifted from one compute node to the other compute node to compute the overall answer, then data transfer is required, and the more data transfer is required, the less horizontal scalable is the graph partitioning strategy. The other important thing is that the different query results should be computed in parallel as much as possible to make a benefit from the distributed setting. And we call this with vertical parallelization. And when I've done the literature research in the semantic web area, then I found out that the common held belief is that the horizontal containment is more important than the vertical parallelization in the query processing effort. The outline of my talk is, first I will give a short introduction into data placement strategies, then I will present you our novel benchmark methodology that is with which it is possible to identify the interdependencies between the data placement strategy and the query execution effort. Then I will give an analysis of the most frequently used graph partitioning strategies, how their impact on the query effort is, and finally I will conclude. So first of all, I introduce some terminology. The assignment of triples to compute nodes is called a graph cover, and all triples that are stored on one compute node is called a graph chunk. These are the 3 common graph cover strategies. One is the hash cover. First of all, you take a triple, compute the hash of the subject, and then place the triple on the compute node where the modulo number of compute node held. The second one is a hierarchical cover. The observation is that the hash cover regularly distributes the triples more or less randomly, and we want to increase the number of triples that are connected with each other on one compute node, and therefore we do not compute the hash on the complete IRE. Instead, we only compute the hash on a prefix of the IRE. And the last graph cover strategy I want to present here is a minimal edge cut cover. As already mentioned before, it tries to reduce the number of minimal edge cut. It tries to reduce the number of cut edges and wants to balance the size of the different partitions. When I looked around how were graph cover strategies compared in the literature, I found out that there are several papers who compare complete distributed ADF stores with each other. Their evaluations are well done to figure out which distributed ADF store performs better than the other. But in order to answer the question, which impact has the graph cover strategy on the query execution performance, these evaluations are suboptimal since it's not clear whether the observed behavior is caused by the graph partitioning strategy or whether it is caused by some other means like a better query optimizer. The other type of evaluations I found in the literature are the ones that use shared storage, like a Hadoop distributed file system, to transfer data from one compute node to the other compute node. And in these settings, you have a higher penalty for the data transfer than in shared nothing systems, where data can be directly sent from one compute node to the other compute node. Therefore, I've tried to develop a benchmark methodology where the only difference is that you can exchange the graph cover strategy and all the rest of the evaluation stays the same. And I will now get into more details about our benchmark methodology. First of all, we use the query generator's plot to generate our queries. These generated queries are Sparkle queries that can be generated out of an arbitrary RDF database. The generation process is configurable by defining several query characteristics that the generated queries should fulfill. One characteristic is the number of joins. Another is the join pattern, which means whether you want to have path-shaped queries or star-shaped queries. Then a selectivity and the number of data sources that should be combined in the generated queries. For the query execution strategy, we did not develop a query optimizer since it is a difficult task to create a query optimizer that would work for every graph cover strategy and would not bias the evaluation in the direction of one specific type of graph partitioning strategies. Instead of having a query optimizer, we create several different query execution plans, like a Bushy query execution plan, a left linear execution plan, a right linear execution plan, and then we execute each query with each of these query execution trees, and then we compare the different query execution trees with each other. As a distributed RDF store, we have developed Coral. Coral is independent of the underlying graph cover strategy, and it was inspired by Triad. It works regularly like this. First you load a data set, and then to reduce the size of the data set, it's first dictionary encoded, then the graph cover is created, some statistics are collected, and then the individual graph chunks are sent to the different slaves, and each slave creates local triple indices on the stored data. And after the loading procedure, we assume that the graph will not change anymore. So when a query arrives, the query execution coordinator is started on the master node and creates then the query execution plan. The query execution plan is sent to all slaves. These slaves process the data on the local triple indices, exchange intermediate results directly with each other, and then the final results are sent back to the query coordinator, who then decodes the results and sends the decoded results back to the client. As evaluation measures, we first focus on the overall performance. For this, we use the query execution time. Then we use the horizontal for the horizontal containment. We measure the data transfer, which means we count the number of variable bindings that are transferred between compute nodes during the query execution. And for the vertical parallelization, we introduce a further measurement, which we call the workload entropy. Basically, there we count the the comparisons of during the join processing on each compute node, and then we compute the entropy over the different compute nodes. And if we combine the workload entropy with the data transfer, we can have an approximation for the vertical parallelization of a graph cover. If the the workload entropy is low, then we have a low vertical parallelization in any case. If the workload entropy is high and the data transfer is low, then we have a high vertical parallelization. But if the data transfer is also high, we have a low to medium vertical parallelization. Then we applied our developed benchmark methodology to compare the effect of the hash cover, the hierarchical hash cover, and the minimal edge cut cover. We used, therefore, a subset of the billion triple change dataset from 2014. There we used the first 1 billion syntactically correct triples. The queries that we generated consisted of 2 or 8 triple patterns. The joint patterns were path-shaped and star-shaped queries. The selectivity was that each of these queries matched with 1 million triples or 10 million triples in the data set. And these queries combine one or three different or combine triples from 1 or 3 different data sources. Our computation environment was one master node with 4 cores and 8 GB RAM and 20 slaves with 1 core and 2 GB RAM. And all these computers were connected with a 1 gigabit Ethernet network. First of all, the graph cover creation time. We can see that the hash cover has the least creation time. The hierarchical cover has a higher creation time since it needs to first identify the optimal length for the IRE prefix that is used, and the longest query execution time has the minimal edge cut cover. This slide shows the overall query performance, but over here we display the relative change in the query execution time to the hash to the query execution time required by the hash graph cover. I want to mention that the y-axis is log scale. As you can see here, for half of the queries, the minimal edge cut cover used twice the time than the hash graph cover. But we cannot figure out regarding between the hierarchical hash cover and the hash cover, which one of them is better. In some cases, the hash is better. In some cases, the hierarchical hash cover is better. And also the differences are within 30% query execution time. For the horizontal containment, we had a look at the data transfer. We can see here that minimal edge cut cover indeed reduces the data transfer between 20 and 40%, whereas the data transfer for hierarchical hash cover and the hash cover is almost the same. When we compare the vertical parallelization, this diagram shows the workload entropy. We can see that the minimal edge cut cover has the worst balanced query workload in almost all cases, whereas the workload balance for hash and hierarchical cover is almost the same. To conclude, the minimal edge cut cover has the longest cover creation time. It has the lowest data transfer, thus it has a high horizontal containment. The minimal edge cut cover has, the minimal edge cut cover has the lowest workload balance. This leads to a low vertical parallelization. Since the overall performance of minimal edge cut cover is worse than the hash-based covers, we would recommend to use hash-based covers instead. When looking at both hash covers, we cannot see a clear winner of both strategies. And another conclude, at least in our setting, the vertical parallelization might be more important for the scalability of the distributed IDF store than the horizontal containment. Our future work is, since we didn't find any graph cover strategy that has a high vertical parallelization, we would assume that if we have a look at historic query workloads and we then want to distribute the graph in a way that for this historic query workload, the workload is balanced and the data transfer is minimized, that we can then achieve a high vertical parallelization for at least queries that are similar to the one in the historic query workload. Then I want to thank you for your attention, and these are these takeaways from my talk.
So thank you, Daniel. Are there any questions?
Why do you say the vertical?
Wait.
Thank you. Why do you say that the vertical parallelization is more important than the horizontal containment?
Because if you have a graph partitioning with a high vertical parallelization, this would mean that you have low data transfer and that the workload of the query processing is equally distributed among all compute nodes. So you can make the full benefit out of the parallelization in the distributed IDF store together with a low data transfer.
I have a couple of quick questions. The first is when you talk about workload entropy, is it correct to think of that as essentially the same thing as load balance? And the other question is, to what extent do you think implementation decisions such as how you are laying out the RDF data in memory would affect your results? So how transferable do you think your conclusions are to systems implemented in very different ways?
I didn't get the second part of your first question.
Sorry, so I was saying you were talking about workload entropy.
Yes.
My understanding from your talk is that is roughly the same thing as load balance. Is that true? So things where when your computation is distributed evenly across nodes, that would give you, I think, high workload entropy.
Yes.
And and when you have poor load balance, you would have low workload entropy. Okay, that's what I thought. And the second question, as I said, was to what extent do you think your conclusions are transferable to systems that are implemented in very different ways, for example, using a very different data layout for the RDF data?
Basically, as shown with his different comparisons of complete systems, there are systems that are much more optimized than other systems, and if you compare them, then the minimal edge cut cover can have better results than the hash cover if you compare them completely. But if I would assume if you would apply the same amount of optimization during the query processing for different hash-based covers, then the database that uses the best graph cover strategy would have the best performance.
Yeah, we briefly discussed this already before the talks, actually. I think RDF has simply some very particular properties which you can exploit for indexing and also has issues with parallel processing. RDF has this unique name assumption, right? So rather than an arbitrary multi-labeled graph, RDF nodes occur only once. The node labels occur only once in the graph, right? So if you have a query, a Sparkle query that has a constant inside, then all the results in the Sparkle query, assuming that it's connected, right, are centered around that node. So then in this case, the locality-based partitioning works very well, but it gives you load balancing, right? So then if you partition the data to one node, then you only have one node that actually effectively works on the query. There's a second very important class of queries then in Sparkle that has to be addressed probably then in a different way. That is basically when you have no constants in the query, but complex join patterns, right? Because then the query results are sort of scattered along your entire graph, right? And some nodes have to process, or many nodes have to process on some of the results of the queries, right? So that's something you might want to consider when indexing as well. You know, so it's probably it was more like a comment then, right? So RDF has some particular properties which you can exploit then as well. To comment indeed.
We somehow already, since the presentation of the paper, we also investigated the graph structure of the underlying graph and how the partitioning, how the different graph partitionings look like. And there we figured out that the poor performance of the minimal edge cut cover was caused by the situation that the dataset has basically a strongly connected core, which is densely connected, and some whiskers that are only connected loosely to the core, and also some other smaller communities that are not connected to the core at all. And the minimal edge cut cover, basically, it cuts the core into partitions, and there are some partitions that mainly consist out of parts of the core, and some other partitions mainly use these loosely coupled whiskers of the data graph. And therefore, when we ask our queries, most of these queries are targeting the main core of the database. So only these graph partitions that contain parts of the core are busy, whereas the other graph partitions that only use or mostly contain only the whiskers, that they have only a weak query performance.
Okay, are there any further questions? Okay, then thank you, Daniel, again for the nice talk.
How careful does this have to be? Is this good enough? Is the mic capturing me? Okay, good.
So, welcome back to the second session. Again, I have to announce it. We have an update in the program. So now comes the keynote of Julian and the two presentations which are originally scheduled at 11 and 11:30 are presented at 2 p.m. and 2 p.m. 30. So let me introduce Julian to you. So Julian Dolby has been a research staff member at IBM's Thomas G. Watson Research Center since 2000. He works on a range of topics including static program analysis, software testing, and the semantic web. He was educated at the University of Wisconsin-Madison as an undergraduate, at the University of Illinois at Urbana-Champaign as a graduate student, where he worked with Professor Andrew Chen on programming systems for massively parallel machines. His work has been included in various IBM products like Rational, AppScan, and in the RDF support in DB2. So he will present a work about towards scalable semantic big data, and now it's up to you, Julian, to see or let us know about the industrial view on this topic.
Okay, I hope the microphone is picking me up. I think we need it, hopefully not for this room, but probably for the live streaming. Without the microphone, it won't work. So first of all, since I'm now up here and I have the microphone, I would like to thank Sven and Lee for this very kind invitation. Coming to SIGMOD has been quite a trip in so many ways, and also, since this was a keynote, it gives me an opportunity, rather than to talk about whatever paper that we just wrote, or whatever product we just threw together, it gives me a chance to step back a little bit and talk about what we've been doing at IBM over quite a while now in terms of looking at the semantic big data, by which I'm going to include both semantics, i.e. reasoning, and also big data as in scalability. So let's look at so this is, whatever, this thing is my phone's being stupid, but I will just look at the, I told it 1 hour, it has no idea what it's doing. Start, okay. So this is over the past quite a few years now, I've worked with a large group of people. This is a long list of collaborators, and at least some of them are still at IBM, and I didn't put affiliations because there wasn't space, and also because that would reveal how many of them are not still at IBM. So what I'm going to do is I'm going to start with a bit of a running example. I'm going to try and work this running example through several portions of the talk where I try to give you a sense of what I mean by reasoning, and how our particular approach to reasoning and then to RDF stores has worked. And then I shall talk about a few different things. So scalable expressive reasoning, that is, I'm going to tell you why semantics is not a database query. And because this is SIGMOD, I figure I should make some inflammatory statements since this is a keynote. Then I will talk about how we use reasoning actually in a real use case, in clinical trials in particular, finding patients for clinical trials. Then I shall switch gears a bit and talk about our works of storing RDF efficiently in a relational database. And finally, I will talk about our latest thing, which has been looking at how we can take RDF data and integrate it with all the other data sources that are out there on the web, accessible by web services. And I shall go back to the running example to show you how you can stitch all that together. So
let's start with, I'm going to start with our running example, and we're talking about some objects in our universe, and because I like to throw pictures up on things, I decided to make I'm going to build a little universe, a little A box, a little data store about artwork. And so we're going to have 3 artworks. This is a Minoan fresco from Crete that's from roughly, 1300 BC or so. It's called La Parisienne. This is at the Archaeological Museum of Greece in Athens. This is what is called Agamemnon's death mask, although for those of you who've read the cliff notes, it's not him. And this is the Starry Night by Van Gogh, which of course is in the Museum of Modern Art. So let's look at our universe. And I don't know why it's got a box, but whatever. So the example we have 6 individuals. We have 3 museums. We have Athens, which is the museum where the King Priam, the death mask is. We have the museum in Heraklion, which is where La Parisienne is, and we have MoMA, which is where the Starry Night is, and we have the 3 artworks. Again, we have Minoan, Mycenaean, death mask, and Van Gogh's Starry Night. Now, the syntax for this is that this is a type. These are type assertions, basically. This says Athens is an individual, an entity of type museum. So we have 4 different types and 6 individuals. And now we have roles. We're only going to have 1 role in our box. These are the edges if you have an RDF graph. They're role assertions if you're talking about an ontology. So we have Athens has the death mask, MoMA has the Starry Night, and Heraklion has La Parisienne. Now, in order to make this an ontology, we are going to have a couple of axioms. And I heard this word at pods. If you've hung out at pods, you probably couldn't avoid hearing about triple generating dependencies. And it turns out that I didn't know this when I was writing the slides, but that's what we have. There are 2 of them. One of them says, if I'm Minoan, if the entity is of type Minoan, it must have an edge to a creation site of type Crete, since my Minoan art is from Crete. And similarly, anything Mycenaean must have a creation site edge to something of type Mycenae, which is another place. And we're going to see, so keep that in mind. We're going to come back to that, and it's going to illustrate why we need what I mean by reasoning. So now let's look at our example A box. This is a graphical representation of the same A box. We're just going to put the museums up at the top, the artworks along the bottom, and then we have the has edges. So if you look at this is obviously not small data. This isn't big data. It's not even small data. It's perhaps tiny or minuscule data. But you can imagine that in the world there are certainly more than 3 artworks, and there are more than 3 museums. And if you had an ontology that tried to capture more of them, this would get rather large. Now, in particular, and we want to reason over this. And so what we have done, the first thing I'm going to talk about is the notion of a summary A box. And so basically this was defined, and throughout this talk, every once in a while there's going to be one of these little, probably unreadable blurbs along the bottom, which is a reference to a paper. The talk is on GitHub pages, so you can, if you're interested afterwards, you can get all the details in these papers. So but basically the idea is we have this function f, which is going to map the entities in our A box to some other set of entities. And in order to actually summarize, it's easiest to think of it as an abstraction function. It's going to take a whole bunch of entities, and it's going to map them down to a smaller set of entities. And in particular, we are going to use concept sets as our abstraction function. So what does that look like? So let's just illustrate that quickly. So now the Minoan, Mycenaean, and Van Gogh artworks, there was each only one entity with that type anyway, so that doesn't change. But the museums, we had 3 museums, and now we have one given with a node for this type. And the edges are done in the obvious way, which is you just take the summary node for the 2 ends of the edge, and you add an edge with the appropriate label. So the museum has 3 has edges to each of these artworks. Oh, and while I'm going on, before I keep going on too much, please feel free to stop me. If anything is unclear or seems just completely wrong or whatever, feel free to stop me. And if I don't pay attention, just, feel free to throw something. So we have our summary A box, and now what we're going to, the point is what we're wanting to do here is do query answering. And in order to do this scalably, we are going to try to do query answering over the summary A box, not the original one, because the whole point is the original one is too big, and things like OWL-DL reasoning, where you can look in the paper for the exact set of things we support. We don't support nominals, I believe. this in reasoning is not something that has tended to scale to very large systems. So the theory we want is the question is we want museums that have works from Crete. That's what the question that we want. And as a human, of the three I put up on the slides before, the obvious answer is Heraclean, right? Since it has La Parisienne, which is Minoan. So, and the other two don't count. So, according to this ontology, the other two don't count, because according to this ontology, the only thing that the museum in Athens has is Agamemnon's death mask, and the only thing MoMA has is Starry Night. Neither of those are from Crete, so they should not show up. And in formal terms, the query looks like this. You want something that has a type museum, and it has something which has a creation site edge to Crete. That's what we want, right? There's a fairly direct translation of the query. And you do the obvious thing to answer the query. Each node in your ontology, you add the negation of the query, and you see if the knowledge set at base is consistent. If it's consistent, that means that node does not have to be an answer, and so we won't return it. If the knowledge base is inconsistent, that means this node must be an answer, because to say it's not an answer causes a contradiction. And as we make whenever we get an answer, the edges and entities in the contradiction itself, the logical assertions that together are unsatisfiable, is going to be called the justification. Just try to remember that. That might potentially be important later. And one thing you can probably see already why I did it this way. This query needs actual reasoning, right? Because all we have in the database is an assertion that La Parisienne is Minoan, and we need the axiom to tell us that means it must have the appropriate creation site to be a match to our query. Because the query is about creation site, the query is not asking directly for things that are known. So what happens here? So when we run, we add the negation of the assertion here. We see museum, and then we have a has, Minoan, and now this edge is dotted because it's not in the database, but a DL level reasoner knows that it must be there because of the axiom, so that's why it's dotted. But together, all of this forms a clash, because if we put a negation of the assertion here, it's clearly of type museum, so that can't be true. And now it has the edge as well, and therefore the museum summary node is causing a clash with the assertion. So the museum. The first thought is, well, okay, so maybe the museum summary node is an answer. But that's actually not quite right, because clearly it's a summary node. So it's not one node anyway to be an answer. And it's clearly not the case that all the museums are answers, right? So the question is, what do you do next? So we look at this. So that's where the concept of refinement comes in. So the idea is we're going to take the edges in the justification. Remember, those are the edges that are involved in the contradiction. And we are going to partition our summary node based on which edges in the justification the individuals that are part of that are represented by that summary node actually have. And let me just illustrate that graphically. Again, so when you take our justification, if the Heraclean Museum actually has this edge to Minoan, right? It has this edge is in the data set. These two, the other museums do not have any such edge to something Minoan. They have other has edges. But when we look at the individual entities that make up the summary, we see that only this one actually has the edge we care about. And so we break our summary node into two pieces, one of which is the ones that actually have the conflict, and the others do not. And so now, after we do that, our new summary looks like this. And now we see that our clash, the contradiction is just on this, and this is actually the correct answer. And these two are no longer have any contradiction because they don't have any Minoan edges. Now, and one thing to notice here is that even when we are reasoning, the summary is split in some sense in a minimal way so that we pull out just the things we need, and the others are left summarized. So clearly, if you only have 3 museums, summarizing 1 into 2 is not a big deal. But if you had a very large number of museums, and you pulled out just a few that were your actual answers, you would retain a lot of the benefits of summarization while still having your query. It's got a glorious interface. All right, so this is roughly what this is sort of attempting to give you a high-level picture, an intuitive picture of how our summarization works and how. Yes?
You're building this into your Sparkle engine, or what level is this being
I will come to that. Actually, this was built, yes, this is built on top of an RDF store, yes. So the reasoning is the backing store that has these entities would be an RDF store, although the way the reasoning was actually implemented is you'd take the summary, once you build the summary, and then you'd load the relevant portions of the summary into memory, and it would do reasoning at that level. But you can also do, as I will see next, you can also do some of those operations on disk as well. So this is giving you an intuitive sense of what it looked like. Now I want to just give you a quick picture of some of the initial results we had with the reasoner. So this share is the reasoner that incorporates summarization and refinement. It stands for Scalable Highly Expressive Reasoner. And K-on2 is another reasoner that was popular at the time that does not. And so you can just, and then the only point of these slides is just to show that the average time is a lot better. And also you can scale to things that are significantly larger when you're using refinement. And that was kind of the point. So that was the first step. And then because I work at IBM and there's this theory that every once in a while perhaps I should try to do something useful, we began to think, okay, we have this reasoning mechanism. Now, I don't do anything useful very often, but there was, what could we do with this? So one of the things that IBM, as you may have heard in the news, is that IBM has been interested in medical use cases now, and it's been interested in that for a long time. And one of the places that we started looking was there was work on clinical trials use case. So the clinical trials are critical for drug development, right? If you have a drug, you need to be able to show that A, your drug doesn't kill anybody unnecessarily, and B, it's somehow more effective than other stuff that's out there, right? That A, the risk is relatively low and there's at least some benefit. And the way so you show safety and effectiveness of new drugs. And so but the trouble is, these drugs are usually designed to treat some condition, right? That there's some qualities a patient has to have in order to be a good candidate to try taking this drug. And so finding those patients is one of the biggest challenges of clinical trials. Right? You need to find a group of patients who meet all your criteria. Now, that's often not necessarily entirely manual in these days of electronic medical records, but it's still often somewhat manual. It does things like consulting physicians, and they have patients, and you're doing a trial, and you know another physician, and you ask that physician, and things like that. And so the result can be lower participation rates than you might like, right? There might be lots of eligible patients, but it might be hard for you to find them all. And our theory was that reasoning should be able to help. And there are three things that make this, a couple of things that make this possible. The first is the trial criteria, at least in the United States, are all online. You aren't allowed to just randomly give people drugs and see what happens, right? There's a whole clinical process for doing this, and part of that involves an actual description of what the criteria for the trial are, what patients are you looking for, and that's often in a semi-structured form. And ones we had were written somewhat in English, but it's very stylized English. I'll show you an example in a bit, but basically they're very relatively straightforward sentences. So you are doing NLP, but it's not the kind of really difficult NLP full of, we're not trying to find out which Paris Hilton stayed in what Paris Hilton or anything like that. We're just trying to find somebody needs a drug, something like that. And the other thing is that medical knowledge has all been formalized. Well, okay, that's too much. Large chunks of medical knowledge have been formalized into ontologies. There's UniProt, and in particular, for the one we use was SNOMED CT, which is it incorporates a lot of knowledge. In particular, this one is useful for us because it has a lot of information about drugs, including their active ingredients and what they do and who makes them and things like that. So what the idea was, well, you take the criteria, you process them, and since they're semi-structured, that's probably doable, and then you run them against medical knowledge. You say, find me who could do this. What patients should I use? And this is all in a paper. Again, there's this little blurb at the bottom. That was a paper in ISWC. And you can see from the years. So I've been doing this for a while. This was quite some time ago. So there are a bunch of challenges. The first is knowledge engineering. So what you have in SNOMED is the relevant medical knowledge about different drugs, how they work, what they do, what their ingredients are, things like that. But what we're looking for is patients. And patients tend to have information in whatever format their hospital has. We were working with a particular university hospital that had its own electronic medical records, and they had their own types representing things that also formed a taxonomy. And so there was at some point you have to manually connect that structure to SNOMED. Now, that's a somewhat laborious process, but on the other hand, it's only done once for the hospital, and then you can use it on all the clinical trials you have now and into the future. So it's this, but you shouldn't, it's not like once you do this, we can now work on any hospital. It would work on hospitals that use a system roughly like that one. There aren't that many, but there's more than one for sure. The other thing is scalability. Now, it turns out that clinical trial criteria often require a high degree of expressivity. They often include things that are very difficult to do in things like, for example, negation. They require existential quantification, and they actually, in some of our systems, they actually required effectively tuple generating dependencies. That was actually needed. So you can't do this with a search. You need reasoning. And we had large amounts of data. There were 59 million assertions that corresponded to roughly 250,000 patients in this hospital. And then there's noisy and incomplete data too. So, doctors write things that are sloppy, and also tests often produce contradictory or uncertain results. And luckily for us, the process I showed you for looking at a clash on a summary node helps you with these kinds of contradictions. So what you do is you start with your data set, you don't add any queries, and you prune out the parts that cause clashes all by themselves, which is what we did. So we started with that's how we sort of used the reasoning mechanism to cleanse the data before we were doing queries. So now we had the thing set up, and let me just show you an example of how this works. So this is part of one of the criteria was a patient on corticosteroid or cytotoxic agent. So this is what I mean by semi-structured English, right? This is not a complicated sentence. This is something that you could probably handle with like a regular expression, or at least some kind of relatively simple grammar. And that's the level of NLP I'm talking about, not a hugely challenging problem. You're trying to read a Wikipedia page and derive stuff. That's not what we're doing here. So, and now we have a DL query, and this is a patient. So we have these are associated observation, role group, administered substance, active ingredient. These are all terms from SNOMED CT. So we basically say you have to have an associated observation that has an administered substance of an active ingredient, which is either a corticosteroid or a cytotoxic agent. Now, there's also role group in here. Don't worry about that. But basically, that is a way of which n-ary relationships are expressed in RDF, right? You have an edge to a role group, and then that role group can have multiple outgoing edges somewhere else. Keep that in mind, because at the end of this talk, when I come back to talk about what we should be doing, that's going to come up. But for now, you can just ignore it. But one thing, you should look at this and you say, this looks kind of like artworks that were created in Crete, right? I have a subtype here, and I have a whole bunch of existentials on the other side. So it's kind of similar. And at an intuitive level, yes, that's the kind of case situation where the need for actual reasoning rather than a database search comes up. So, and all of the queries look something like this, and I threw in this number 00419068. I threw in that just to make it look real. This is actually the number from a real clinical trial that was available on the NIH website at one point. I imagine it was long ago. It's probably gone by now. So let's just look at some results. So we have 9 queries here. I think there are 9. There should be. Yes, there are 9, I believe. And you can look at the matches. This is the number of individual patients who would potentially be appropriate for this clinical trial. This is time. Time is in minutes. You notice that most of them take up to an hour. Some of them a couple of them take quite a bit longer. Now that might seem slow, but remember, the alternative is there are 250,000 patients here, and the alternative is somebody is looking through them somewhat by hand. So they would not be able to do that in a few hours. So by that standard, this is, compared to the alternatives, this is blazingly fast. Now, the last column over here is weakened, and so what that means is whether or not all of the criteria for the clinical trial were completely captured in our mapping from the university hospital's taxonomy and patient data to SNOMED. Now, we were building this as a research project. You can notice several of the queries, the majority of the queries, we just took the whole thing and we didn't have to weaken it, everything mapped properly. Several of them there were basically pieces of the criteria, clinical criteria, that were not captured very well by our mapping from the university hospitals records to SNOMED. So that means we just left those parts out, because obviously if you can't find, you won't get a clash if you don't have the data you need. But the bottom line is the majority of the queries were not weakened, and compared to doing it by hand, it was much faster, and it got noticeable numbers of patients in most cases. How many, 2 is probably not enough for a clinical trial, but 74 quite possibly is, right? Yes?
When you give the times, those are on a large server or a laptop, or what sort of?
Those are on, I wouldn't say a large, I would say, a sort of a work group kind of server class machine. It's, a few gigabytes of memory, high-end processors. So we're not talking about a supercomputer, but we're probably not talking about a laptop either. It's definitely the kind of thing that if you're an enterprise, you have machines lying around, that would be sort of the class that we're talking about. So this is sort of where we went with this was presented at ISWC, and this is sort of where we went with the reasoning work, and this is this is sort of the point. The point here being that, as you saw from the previous slide, the queries are actually reasoning here. We're not simply looking at searching a database. But in terms of that, so now let's switch gears slightly and talk about, you'd asked where is this ontology stored? What is going on? And the answer is there's a relational store. And now I'm going to switch gears. I'm going to talk about the work we've done on the lower level, which is actually an RDF store for the data. Now, there's a slight caveat here. You might think, oh, so is this the RDF store that the other experiment was done on? And the answer is no. We haven't, all of the pieces that we've built haven't entirely been integrated yet. And I'll come back to that at the end of the talk too. But the point is, there are lots of large RDF data sources. We've seen other talks have said, they've thrown out numbers like 50 billion triples, whatever. But even if you took a single data set you wanted to reason on, DBpedia has more than 300 million triples. If you get the billion triple challenge, it's well over a billion now. It's like 3 or something. Last I downloaded it and did WC, it was something like that. And so what we want to do to store this, we want to exploit scalable RDBMS technology, right? In terms of databases, the relational databases out in the world, these numbers aren't enormous. They're fine. They're not tiny by any means. It's not like you could load it on your phone and query it in SQLite or something. That's not going to work. But if you had, like inside IBM, we have DB2, Oracle has Oracle. These things support serious query optimization, transaction support, and concurrency. So when you get a large data set, they tend to go to town on doing the query in parallel and being relatively efficient about it. So that's what we were trying to do. And then this is currently embodied in a system called Quetzal, which is on GitHub. And these slides are all on GitHub too. So you don't need, if you don't bother to write things down, I can give you a pointer to the slides. And again, in the interest of being at IBM and trying to convince them that every once in a while I do something slightly useful, this code actually shipped in the RDF support. Well, not this code, but the version derived from this shipped in the RDF support in DB2 version 10. So,
even on mainframe edition?
No. So. Yeah, you're right. DB2 is multiple editions. It's basically all unified except Z-series at the mainframes. And so we're talking about basically all of DB2 except what's on the mainframe. So PowerPC, Linux, Windows, all of that stuff. But not Z-series, that's correct. So let me tell you, what are the challenges here? So we say, okay, so this is good. Deep databases they're cool. Why can't we should just use them, right? Well, there are a bunch of things that make it a little bit challenging. So one of the things that databases like is a schema. And one of the things that RDF doesn't have, really, is a schema. It has RDFS, RDF schema, but that's not the same thing, right? That isn't rows and tables and columns and whatnot. So the set of properties depends on the data set. And RDMS, DBMS typically require a fixed schema. Schema changes tend to be catastrophic events on databases. Adding columns, this is not something that your database is going to be happy with you if you do that. So we have to not do that. But what we are going to do is kind of pick a compromise where we're going to tailor a data set, tailor the schema for a data set, and then not mess with it. And now Sparkle queries are a declarative graph query language, and what we do is we translate Sparkle to SQL to retain the benefits of database technology. We're going to be generating SQL queries. Now, in this talk, I'm going to be focusing on the top bit. I'm going to try and show you what the schema is that's more different, I think, but I'm certainly happy to answer questions about the Sparkle translation as well. So let's go back to our example data set. I told you I was going to try and work this through all of the portions of my talk. And I'm going to add one more piece. And this is going to, the excuse for this is going to will show up later. We have each museum is going to have a location. And each location is going to be identified by its longitude and latitude, and that's all. So we have instead of 6 objects, we now have 9, and then we have 6 literals here along the top. So what are we going to do with this? Now, the Quetzal schema is what's interesting about it. Oops, I hit this arrow thing. I should have mentioned probably this work all appeared in a 2013 Sigmod paper. Now let me go back to where I was before. So what do we do? What is our schema? The schema, we call it an entity-oriented schema. And the idea is this. We're going to take the properties for a single subject. So if you have subject, predicate, object, triples, we're going to take all of the triples for a single subject and try to stick them on a single row. And so we're going to have rows for predicates and values. And then when you have a predicate with multiple values for the same subject, we're going to have there's a secondary table. Details about that are in the Sigmod paper. I've contrived my example to not have this because the secondary table is annoying to fit on a slide. And the point is to fit entities into limited database rows. One of the key challenges that generally there are way more predicates than available rows. Even a simple data set will have hundreds of predicates. DBpedia has 30,000 or something, and that was a while ago. And on the other hand, predicates tend to typically be somewhat associated with types. It's unlike, if you have 30,000 predicates, you're not going to have an entity with 30,000 edges. That's extremely unlikely. Typically, and beyond that, some predicates like type are essentially universal, more or less everybody has them. On the other hand, many predicates are not. Many predicates are specific to particular classes of entity. And to us, what that said was we're going to use graph coloring. So for different kinds of entities, we're going to use graph coloring to figure out which rows we could use for which predicates. And we're going to spill onto multiple rows only when necessary. There are analogous tables in the reverse direction, which I won't show. That is why subjects. You could also have the same thing for objects, and we do. But I'm not going to mention that because, again, in the interest of fitting things on a slide and because it doesn't fundamentally add anything. It's the same basic idea, only in reverse. So let's just take a quick look at an example here where this is the same running example we've had before. We have the artworks, La Parisienne, Death Mask, Starry Night. We have the museums, Heraklion, Athens, and MoMA. And we have the 3 locations. And each of them has a type. So you can see type is given the input in the first row. First P1 and V1 here. It's types. Everybody has them. And some of the others, now the artworks, because this is an example designed to fit on a slide, don't have any particular properties. You might think they would. They might have pictures or whatnot, but we're not going to model. We don't need to model that right now. And then the museums have 2 things, right? They have a has for the particular artwork that they have. And these are dots just in order to stop things scrolling off the edge of the slide. And they have they're each at a particular location. And so we're going to use positions 2 and 3 for the has and at relations, respectively. And then for the locations, they have latitude and longitude. And again, we're going to have we're going to use positions 2 and 3. So this is an example of how coloring figures out that even though we have more predicates, we can compress it into our schema. And this also allows you to, depending on your predicates, this also allows you, if you're looking to do search efficiently, sometimes if you build an index on some of these columns, you essentially get an index for multiple predicates with one database index too. So let's just look, so that was the schema, and let's just take a quick look at some data to show you that the performance is plausible. So this is time in milliseconds, it's a log scale, but so it's milliseconds, so 1 to the third, this would be 1 second, I believe. And you can see when we're comparing R2DF, which is our schema, to two other reasonably well-known systems, Jenna, which is a bit of sort of a reference implementation, really, of Sparkle, and then Virtuoso, which is our reputed high-performance RDF store. And you can see that the performance, there are trade-offs, but mostly we do relatively well. Sorry? These are measures of time in milliseconds. Oh, right. These are, this is, I believe, 100 million triples. So, and again, this is not running on a distributed cloud. This is running on the kind of server that you might have under your desk if you worked for a large enterprise. So that was the query build, and you may notice I should probably have mentioned this. Well, actually, let me go on. So this is, and you can look here. You look at the queries 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, and 14. So you might say, well, what about 11 and 12? So those are the queries that actually require reasoning. So in these queries, we are evaluating in our RDF star Sparkle engine, and you cannot express those queries conveniently in Sparkle. Well, you can, but you get you get 0 back because it doesn't have the appropriate logical. It doesn't do inference appropriately. So that's just an example of. At this point, we've switched gears a little bit, and we're really measuring the performance of a Sparkle engine, and on the. And so and again, the other thing, as we were using this database to try to look at different use cases in Sparkle, one thing that we quickly noticed is that there's really data everywhere these days, right? There's numerous structured data sources available. There are things like DrugBank and Uniprot and DBpedia. These are all data in RDF that you can get a dump and you can download it and you can build something. You can run it. We've used all of these actually in Quetzal. But data is increasingly diverse. You have other formats often nowadays. You have XML, JSON, CSV, whatever it is, and you find data sources that are really not available directly to you if you're just purely an RDF store. For instance, if you imagine trying to look up, if you imagine doing some RDF queries, you get some location information, and now you want to look up something on Google Maps. You can't download Google Maps data, right? It's much too big, and B, that's their business, right? They're not going to give it to you. But the fact remains that we can do powerful things if we can integrate all of this data together in some way to use it along with data that we have in our ontologies in RDF. So the plan is to reuse and extend existing declarative Sparkle. And I should actually say, why are we doing declarative Sparkle? If you look at, there has been a bunch of trends in things called property graphs, and people have done things like using these languages called Gremlin, where you essentially integrate a bunch of Java code. And then in theory, you could presumably make calls to their APIs and get data, and you could put it all in a hash table and mess with it. But now you've really lost, now you're writing a program. You've really lost the ability to actually write a query in any meaningful sense of the word. And we wanted to preserve that, partly because you get to exploit the power of optimizers and analysis and engines like DB2, and also because not everybody in the world wants to learn how to write these programs if all they want to do is query their data. Now this work all appeared, this is the last shout out to my own work here, this all appeared in a paper presented at ISWC last year in Kobe. So let's look at an example. What does this mean? So there are two issues that are going on here. I'm just going to go to the time 11:39. So the first thing is, as we are constructing these web services, one of the issues is that the queries are likely to become larger and more complicated. And that's going to stress one of the current issues with Sparkle, which is it's very difficult actually to modularize Sparkle queries in a good way. If you see the examples, you write select, where, and you write a whole bunch of stuff. Now, you don't have, if you have reusable pieces of a query that you'd like to pull out, that is actually quite difficult. And if you use some of the things that are there now, they tend to, there's a whole bunch of extra XML machinery. There's one system whose name is now escaping me that actually reifies all of this into its own bunch of SPARQL statements and becomes relatively cumbersome to use. And we wanted the lightest, a lightweight mechanism. And in fact, what we ended up, we wanted something like this. You say function museums with. So I have a type, and I'm going to get a museums and latitude and longitude, and it does the obvious thing. Assuming you bind type, you will be able to figure, it will, it puts in the appropriate tuples that you need in order to tell you this museum has this type of artwork. And this is you could imagine using this in multiple queries depending on, I mean, this is obviously a simple example to fit on a slide and to use our data set, which only has nine objects in the first place, but it's sort of an illustrative of what we were trying to do. And we introduced these, and we introduced an extension to the bind mechanism where you can give it the left-hand side here, and then it will just, and you can tell it that it will compute the things that you wanted. And it actually, because of course when you're using it purely in SPARQL, clearly the left and the right-hand side are not different. And the technical details of all of that are in the paper. But it's convenient, it's often convenient documentation really to think about setting it up this way so that people understand what it is you would be expected to be supplying. So let's look at an example web API. So that function is purely in SPARQL. That's about modularity. But now, let's say we wanted to look at data outside. So one trivial web API I found, which is quite useful for this talk, is ipapi.com. And what it does is it basically, all it does is it knows where, it looks at the IP information. Most phone companies will tell you stuff, and actually many Wi-Fi hotspots actually know where they are, and they make that information available basically to anyone who asks. If you come from somewhere, if you are using a hotel Wi-Fi, anybody can easily find, and you send somebody a request, they can know where you are and where you came from. It's very easy, all of this. And this is in particular, if anybody was using the hotel Wi-Fi here in the Hilton, it's apparently run by AT&T, and it's in Chicago, of course. There's longitude and latitude, Chicago, Illinois. And so if you thought maybe I'm on this anonymous hotel Wi-Fi, no, nothing's anonymous anymore, right? So this is an example, and this is the kind of data we would like to use to integrate with RDF data that we have. So let's look at a trivial example. First we're going to encode ipapi.com in the syntax that we proposed in our ISWC paper. It throws back XML, as we saw on the previous slide, and these are XPath. Query tells it where the root is. It extracts the query from the XML, and then you look at it takes these two longitude and latitude fields, and those get bound like this. And then we use the same bind syntax. They look just like any other function. We use the same bind syntax to say it takes no arguments and it will return you a latitude and longitude. So now, and this is clearly this is the kind of thing that it's going to, if you're on a mobile device, it will basically throw us back where you are approximately. So what would you do with this? So let's put together one of those examples. I want nearby Minoan exhibits. Now, so I'm talking about the web. I got this, I got that, and I only have 9 triples, right? So we have to be a little bit creative here. But, so the RDF is the stuff I was showing you in that previous table for the museums. And we're going to use ipapi.com to get a position. And we're going to say, first we're going to bind the museum, the latitude, and the longitude to say what museums have Minoan exhibits. And then we are going to bind get position to say, where am I? And then we're going to do a filter that says, only return museums that are near me. And now this is, of course, a completely stupid way to define near me, right? There are whole schemas for spatial positions that will do a better job, right? And you can't even use Euclidean distance because the Earth is a sphere and so on. But there's the right way to do it, and then there's what fits on a slide, which is what I'm using. But basically, this is the rough idea, right? I would get a... this allows me to ask... I mean, we almost have a mobile app. We almost have a mobile app right here, right? If you enter an artwork, type of artwork, and we can just do the whole thing as a single query. If you imagine doing this as another piece of code, you'd have a script that would find your position. It would take the numbers. It would try to contrive a query. It would do this. It would do that. The point is we were trying to make it more declarative like this. And this way, you're now exposing things like this to the optimizer so it could get a sense of which thing it should do first, how to arrange the temporary tables, things like that. So then you're giving more scope to the optimizer as well, rather than making the application developer also do the query optimization in his head. So that's sort of the last piece of code that we had talked about. I want to just say one more quick thing, which is the paper that appeared at ISWC didn't just talk about museums in ipapi.com. Actually, I only found that site when I was making this talk. What we actually had was a web service use case for drugs. So that was integrating things like drug bank. So it's a drug, it is an XML. It's got a lot of information about drugs. There is information also out there from Uniprot about drugs to the transporters, which are proteins that the drug uses to have an effect on the human body. And then there's another package which takes drugs and there's a notion of its chemical structure, which is called SMILES. So all of this information is available on the web. Some of it is not available in RDF. Some of it's available in RDF. Some of it is some of it is actual programs, and a lot of it is more convenient to access via various different kinds of web services. So more detail about all of this is available in the paper. But the point is this, rather than we've actually constructed, and again, it's an actual healthcare domain kind of application that uses the integration of web data into our query language. So now I want to talk, I'm almost done, you're almost free, but I just want to say a little bit about some ongoing work that we have. So we looked at the Quetzal store that I showed you, those numbers, they all came from DB2. But one of the things that you can't help but notice, especially if you go to a database conference, is things like column stores are increasingly popular. And one thing we have been looking in particular at Google BigQuery and trying to adapt the entity-oriented schema to a column store. And one of the key differences, I think, is that the number of columns, obviously, in a column store is potentially a lot larger. DB2 has a fairly tight limit on the number of columns you can have. BigQuery's limit is something like 10,000. So if you have, for many data sets in RDF, you would simply be able to use one column per predicate. And all of these databases have also tended to go to town on allowing structure within values in columns. So typically they allow arrays, they allow JSON, and we are using that repeated values in a column, and we're getting rid of the notion of the secondary table, which I didn't show you anyway. And currently, and we have no reverse tables because so far we haven't started needing those yet. Currently, this is ongoing work. We've implemented it in the Google BigQuery. We have a loader. We can take the data and convert it into our schema conveniently using the pipeline structure that they have in Beam. You can read in the data, you can do the transformations you need, and then dump it into BigQuery directly. And some parts of Quetzal are functional, but not enough to be very usable as yet. And now we get to the end. So what does the future hold? If you look back at some of the things I said, you say we have reasoning, we have an RDF store. We don't actually have both put together at this point. That would be something to fix. But also, the other thing one of the things you look at with property graphs is that people keep talking about edge annotations, particularly like a timestamp, for example, on a property. And if you think about, in one of our currently ongoing projects is we want to figure out how to extend our schema and our properties to enable this sort of thing in an RDF store, especially as column stores support structure within values in it seems promising to consider whether you can put the edge annotations into that sort of structure in a way that still allows you to do efficient querying. And ultimately, I'm going to claim semantic big data has got to mean reasoning. We're not a database. If we're a database, what are we doing? I mean, my ultimate holy grail is to put the summarization refinement code into Quetzal, because I believe that the entity-oriented schema is going to be very good for building our summary, since our summary is looking at the concept sets across single entities. If we put all this information about an entity in one place, on one row, it's going to be easier to build the schema. Now, and for both of these both probably sound like work, and they are, and of course we would love to get others involved. That I had given you earlier on the slides the GitHub site for Quetzal, so we'd absolutely love to have people work with us on building any of this. And with that, I am done. Thank you very much for listening, and of course, once again, thank you all for inviting me to SIGMOD.
So we have time for plenty of questions.
Thank you for the nice talk, but can you tell us more about the shape of the rewritings? Because when you rewrite Sparkle into SQL, so what are the shape of the rewritings? What features of SQL do you use? Do you use, for example, do you use views or for more recursion, or do you use UCQs, or you have alternations between disjunctions and conjunction, and what is the depth of this alternation?
Okay, so I don't need the microphone. I've got one. See, I get to stand up here and yap through the microphone. You guys are the ones who have to pass it around. So basically, it sounds like you're asking roughly about how query planning and execution works. And so basically, what we have, the way I didn't talk about, that's the one thing I didn't mention. Basically, what we do is we have a planner that looks at the different pieces of the Sparkle query, the triple patterns, and it uses a greedy algorithm to figure out the order in which it wants to do these things, and essentially those get turned into a series of common table expressions for the database. So if you have 3 triple patterns, you're going to have a couple of common table expressions to compute the intermediate results, and then you'll have the end. In terms of disjunctions, if there's a union, we generate a SQL union for that. Optional is slightly more complicated, because optional effectively becomes a left join and an outer join in a funny kind of way. And so we have those, and Sparkle 1.1, we support things like filters with nested queries for filters, and then the other thing that we have with 1.1 is property paths. So a property path, we do not actually use recursive SQL directly. There's a translation step that turns it into it uses something. What am I thinking? Magic sets it. Yeah, no, it doesn't use a procedure. It turns it into pieces of SQL, but it has to break it down. If you use recursive SQL naively, typically you are not going to be happy with the result, has been our experience.
Thank you for that very interesting talk. My research is in bioinformatics, so the healthcare applications you showed there were very intriguing to me. Especially the first one where you're connecting patients to clinical trials. Would you say that semantic similarity, some measure of semantic similarity to compare the patient's attributes to whatever attributes are required in the clinical trials, would be more relevant as a solution to that problem?
No, I wouldn't. And the reason I wouldn't is that many of the clinical trials criteria involve things like a patient being on a drug with a particular ingredient. Now, the drug itself has various links. You typically, the patient record will tell you something about the drugs, often encoded as like a brand name or something. And from that, there are multiple hops through the data, usually to figure out that it has a particular active ingredient. So if you look just at a very local similarity, I think you might end up missing a bunch of things that are easier to find as when you have when you're doing reasoning and you're potentially exploring the graph in both places.
But that's what semantic similarity does as well. It doesn't look at exact similarity, but some measure of partial overlap within the DAG structure while doing reasoning.
So that depends on, it's going to depend on, but you were talking about the semantic overlap of the properties of the particular things
Yes.
involved. Now, as long as you're talking about semantic similarity in terms of, it's beginning to sound a lot like reasoning.
Yes, so
So
semantic similarity does.
it may not be so different, actually.
Right, that's what, yeah.
And the one thing to be careful of, though, is at least in the way the way SNOMED was encoded, it did require the kind of triple generating dependencies that I showed at the beginning of the talk. That there are parts of some of the similarities are actually implicit, and it took and we needed the reasoner to expose them. So I think
Yes.
semantic similarity would need to
Work with the
find a way
reasoner?
to do that as well.
Yeah, yeah. Thank you.
Yeah, thanks. So I was curious about your summary nodes. So in your example, it seemed like a summary node is a class, and so in the ontology. And so my question is, is every class in the ontology a summary node? How do you decide that? And do you do, say, intersections or unions to define maybe better summary nodes? And then could one just come up with clusters and name those as summary nodes and that have nothing to do with the ontology?
Okay, so the question, so in terms of whether a class is a summary node, the answer is no. The summary nodes that we were using were actually concept sets. Now, because I wanted everything to fit on a slide, each node had exactly one type. So all of the concept sets are of size 1. So in that case, it's the same thing. But for example, in the medical data, there were plenty of nodes with multiple concepts. And so then they would form different summary nodes based on essentially the different sets of concepts that you had.
So that meant intersection.
Yes, that would be correct. It would be I'm this and I'm that. So yes, that's right. It would be an intersection. Now, the formalisms behind the summarization and refinement are actually fairly general. And there are a few properties that function f, the summarization function, has to have in order for our summary to actually work. But it isn't necessarily related to concepts. So if you chose to define clusters in some other way within broad limits, yes, that would be fine. Obviously, the summarization is only useful if it reduces the number of nodes dramatically. Otherwise, I mean, you could map every node to itself, but that's not a very interesting summary. But within limits, yes, you can define it almost any way. Concept sets are the only things that we have experimented with.
So suppose we wanted to build a Sparkle engine or some sort of inference engine that had both reasoning and the ability to query underlying RDF database. That is, reasoning over very large triple sets, essentially. Has anyone done that? And what sort of architectures are people using? I mean, my impression is that most reasoners run in main memory.
Yeah, I believe that's correct. Okay, so your question, okay, so I believe it is correct to say that most reasoners run in main memory. I know of at least one exception, which is our stuff. Now, which is our stuff. The reasoner I showed you, share. So if you think about the refinements, let me just go quickly back to the refinement step, if I can figure out how to use this thing. Yes, I can, and okay, where's refinement? Where did it go? Wait. Here, let's look at this one. So if you look at this, what we're basically doing here is we're computing which individuals in the summary have the appropriate edges and which do not. Now, we did initially start with that computation being done in main memory, but when we got to the clinical trials use case with 250,000 patients and 59 million assertions, that didn't work terribly well. And actually, we wrote that computation as a series of queries against the underlying database. So we no longer required the entire store to fit in memory in order to do our reasoning. So that's why I say our reasoner did not necessarily run in main memory. Now, that being said, the entity-oriented schema that we now have, we believe, is much more scalable for SPARQL reasoning than the older triple stores that we had in this context. And we have not yet put this reasoning mechanism on top of Quetzal. But that is definitely something that, in order to answer your question, that is what I would do. I would build Quetzal, I would build this mechanism on top of Quetzal. I believe that should make reasoning dramatically more scalable than we have seen before.
Okay, maybe I have also one question related to this. So you say, okay, semantic big data means reasoning, but in the beginning you said, okay, DL reasoning is costly, is not performant. Please correct me. And you show some techniques which not directly do DL reasoning on the whole data. You know, and maybe, yeah, you show some indirect mechanism to overcome some problems, but they are still stuck to batch processing, I would say, because they are some minutes, 60 minutes or something on big data. Are there any plans in IBM to overcome, yeah, DL reasoning problems with big data somehow, so that you have interactive query processing, something like that?
Well, so let's step back a minute. So reasoning doesn't perform. So that's not entirely what I said. I do think it's the case that, as far as I know, approaches like summarization are the best hope we have to make reasoning perform scalably. Now, and I definitely showed you the clinical trials results that it does scale, but as Sven correctly points out, 30 minutes, 60 minutes, 70 minutes, this is not interactive. Now, keep in mind that the alternative is somebody going through 250,000 patient records by hand. And what I said was, compared to that, reasoning is blazingly fast. So it really depends what you mean by performance. If you mean, are we going to get an enormous data set, full OWL DL, billion triples and sub-second responses so that you can throw it into a web app, my answer would be no, not anytime soon. I don't know how to do it, and I don't think anybody else does either. But on the other hand, I don't think that is the only, and on smaller data sets, we can show reasoning can perform well. And I think we do have to be realistic. If you have 250,000 patients, it's not at all clear that sub-second responses, I mean, it's going to severely limit what you can actually, the questions you can ask. If you need a fast answer, you can't ask a complex question over a very large data set. That's probably not going to work. But I think there are many, so I think there are situations where we can give you interactive response, like LUBM, the simpler queries, we were showing we can show very quick response time, sub-second, some handful of seconds. Now that's not a particularly deep reasoning. But I think, so I guess my bottom line would be, I think we do have to be realistic. I think the reasoning is going to be, as I said, I argue that the reasoning that we do is really, really fast compared to the alternatives. And I think we need to keep that perspective, that you can't ask an impossibly hard question and expect a reasonably fast answer. That's just not going to happen. But it doesn't need to either.
So one last question, we are already over time.
Thanks. So I'd like to ask you sort of an obnoxious question, if you don't mind.
Not at all. If you don't mind an obnoxious answer.
Yes. So, so in your clinical, study example, one alternative, which is the alternative that I think most people would use, is to throw all the clinical data into some JSON representation and write a Spark job. that, looks for specific, things inside each JSON document. And that probably would run very, very fast on 250,000 documents.
Absolutely, I agree.
And so, there's the engineering of doing that. But there's also, of course, the engineering of getting all this semantic stuff to actually work. Defining all the rules, making sure that the data is clean. So do you have a sense of how those two things compare?
I would say that the alternative of dumping everything into a JSON store, you need to compare like with like. You need to say, if I'm dumping, I need to be able to get the right answers still. So all of the semantic information that actually requires triple generating dependencies, that has to be done somehow into your JSON store, or you're not going to find quite a few of these patients. So you can't get out of reasoning just by using JSON, because that's where the answers came from. As far as preparing the data, I don't know. One of the things that made the reasoning process option very attractive to us was that things like SNOMED CT have been built already. And so all of the medical knowledge, the reasoning that we needed to figure out that this patient is relevant to this trial due to properties of the various drugs and other things involved, that had already been formally specified. So using it was a relatively straightforward option for us. If you want to dump all this into a JSON store, you're going to have to find some other way to get that data. So I hope that was obnoxious enough.
Okay, a very last question.
So my question is a little bit related to your query refinement here.
Okay. My favorite part.
And that is, it's often seemed to me that one of the frequent cases in which you would want to use a little bit of reasoning on, say, a hierarchy is when the query refers to pieces of an ontology that are being used as a classification scheme. And it seems to me a very common kind of query that people want to ask is, instead of asking about, let's say, individual kinds of automobiles, you want to ask about a class of automobiles. And you want to have automatic expansion using an ontology. So maybe you want to say, SUVs. And then you have a taxonomy of brands of automobiles that say, well, this is an SUV. And maybe you want an SUV with 4-passenger capacity or something like that. But it seems to me that oftentimes the reasoning part of it refers to an ontology which is much, much smaller than the instance level of the patients. And it seems to me in that case that it ought to be possible to do the sort of expansion of the classification stuff in memory and then do the instance level querying using some RDF store or database or something like this. Have you thought about that in terms of a class of queries and a kind of inference that people might commonly want to use that you could build a hybrid system for?
Yes, and it's interesting that you use the word hybrid system. So that's absolutely right, and we are not the only ones who've thought of it. That's where classes of ontologies such as EL+ are defined. Basically, a lot of the more restricted ontologies, reasoning classes that aren't full DL, are designed to help you specify exactly that kind of ontology and reason about it. And there is a different approach you can use to reason in some of those cases, sometimes called query expansion. Basically, you take your query, you take your taxonomy, and you expand all the possible ways in which your query could be matched by subclasses and subtypes of different kinds. Yes, and in fact, we have indeed built that. That was something I didn't have time to get into. Particularly in our healthcare domain, while some aspects of it do require actual reasoning, triple generating dependencies, you need those, but you don't need them for everything. And sometimes you need exactly what you described, which is a taxonomy. And we built a hybrid system. I like the fact, see, I picked up, you used the word hybrid, so I was very happy. So we built actually a hybrid system that would do the expansion, figure out the answers you could get that way, and then only in the other parts where you really need reasoning would it actually go back to this mechanism. Yes, we have built that. And yes, I would say in a practical system, that sort of approach is definitely one that would likely be good in many cases. But I do think if we're going to do reasoning, ultimately there will be places where we need to do it. So I think that what you talked about of the hybrid system, that's what we built, and I think that is the thing that probably makes the most sense in practice.
Okay, thank you, Julian, for this nice talk.